Hello,
My name is Ashish Rajaman.
and my name is Umang Srikumar, and we are part of group B27. In this part of the video, we will break down the MATLAB code of the E-shaped ultra-wideband patch antenna and all its components.
First, the physical constant was used as a means of conversion between millimeters and meters. We begin by defining the thickness of our structure in the z direction and the branch gap of the structure. This represents the width of the left branch in the x direction, whereas the height of the left branch is represented in the y direction. The width of the middle branch is represented in the x direction as above and has the same value, whereas the height of the left branch is represented in the y direction. The top branch and the bottom branch are identical in proportions. The width in the x direction, and since the top and bottom are identical, subtracting the middle height and the branch gaps results in the height of both the top and bottom portions combined. Dividing this value by 2 results in the height of the top and bottom individually. The next few lines of code represent the setup for the substrate. For our design, our substrate consisted of 4 cells.
The dimensions of our sim box was set up to contain the complete structure of our E-shaped patch antenna. This represents the center frequency of our patch antenna, which is the frequency of the excitation. FC represents the corner frequency, 20 decibel cutoff frequency to be specific. This was used to initialize the finite difference time domain for our excitation. A Gaussian type excitation was used to induce the light pulse to a range of frequencies. And this line represents the boundary conditions. C0 and F0 plus FC represent the lambda, which is then divided by 20, and this gives us the cell size for our mesh.
This was used to set up the CSX CAD geometry and the width in the x direction, y direction, and the z direction.
This was used to build the left part of the E-shaped patch antenna. That would be that part. Whereas this was used to build the top part of the E-shaped patch antenna. So that's over there. And this was used to build the bottom part of the E-shaped patch antenna, which is over here. As well, this was used to build the middle part of the E-shaped patch antenna, and that's right there.
The code defined here was used to add dielectric elements from our previously defined substrate properties. First, we create a basic substrate material using this line. We then give the created substrate our previously defined substrate properties.
We now create a ground component using the same dimensions as the substrate defined above. This line creates a perfect electrical conductor. A ground 3D box model is then inputted as seen from this line. The simbox's size is then reduced for the near field to far field box. And finally, we then create a near field to far field surface dump box.
At this point, the simulation folder is then prepared externally. Any existing simulation is cleared and a fresh simulation is ready to begin. An empty simulation folder is then created. This line displays the structure in the OpenEMS window. The following line boots up the OpenEMS software. The next few lines reads port voltages and currents in the time and frequency domain while correcting the half-time step. The next few lines of code represent the feed point impedance. The feed point impedance is now plotted. The variable Zin is assigned the value of the feed point impedance. This line represents the real part of the impedance, whereas this line represents the imaginary part of the impedance. The title, label, and the legend is applied to the graph, and the graph is then plotted for the feed point impedance. Moving on to the S parameter, calculating the reflection coefficient. The reflection coefficient represents the amplitude of the reflected wave relative to that of the incident wave. The variable here, S11, is then assigned the value of the reflection coefficient.
We now plot the antenna parameters. The first step is finding resonance frequency from the reflection coefficient. This calculates the far field from the range phi equals 0 degrees to phi equals 90 degrees. The field at radius r is then evaluated. E far theta is the theta component of the electric field strength at radius r. E far phi is the phi component of the electric field strength at radius r. P rad is the time average radiated power. D max is the maximum directivity. As you can see, all these values are now assigned to analyze the near field to far field. And this line is just to convert D max. Power and directivity are both now displayed, and the E field magnitude for phi equals 0 degrees is calculated from this for loop here. We now display the polar plot. The E field magnitude for phi equals 90 degrees is calculated using this for loop. And finally, the polar plot for the above mentioned phi is now displayed. What you see before you is the implementation of our MATLAB code provided as an open EMS structure form. As you gaze upon the structure in all its glory, you will see multiple layers. The top layer being the model for the E-shaped patch antenna structure, also known as the patch. The gray layer being the dielectric, which we had defined all of the properties for, all substrate properties, and the bottom layer being the ground. Finally, a feed point is inserted into our structure. The feed point is drilled directly through the center of our structure. It is first drilled through the ground layer. It then is drilled through the substrate layer until it is in contact with the patch on top of the substrate layer. This procedure allows us to properly excite our ultra-wideband patch antenna.
We'd like to thank you for watching our video,
And we hope you've learned plenty of information about how to program the ultra-wideband E-shaped patch antenna and all its properties.